right, today's new hypothesis test is for a proportion. So I'm going to call this z-test for a proportion. And that kind of gives away what distribution we're utilizing because it's a z-test. Okay? So every time we have a new hypothesis test, I have to go through two things. What distribution does it utilize? Here it's the z-distribution. And then the second thing, of course, is I'm familiar with the z-distribution. I know how to do critical values or p-value if I have to. And the only other thing that I really need is how to do the TV, or the test value formula. Okay. All right, so it's going to be z equals, because it is a z-distribution, p hat minus p divided by, and then a big square root, and then a pq divided by n, and all of that is under the square root. Okay, so make your square root really big to encompass all of that fraction. Okay, now what I'm going to do is I'm going to put a little p naught here, because I want you to associate that with what you have in your null and alternative. And also here, and also here. Okay? So I want it to be clear in your notes that this guy comes from the sample. And all of these guys come from the hypothesized value. Okay, so make that clear in your notes. This guy p hat comes from the sample. This p, and this q, that all comes from the hypothesized proportion value. Okay? And of course, n is sample size. And as a reminder, when we did the confidence interval, what p hat stands for is x over n. Okay, it's a percentage or a proportion. And sometimes they give you the actual sample units. So x is the number of sample units with the characteristic of interest. N is the sample size. Okay? So again, x is the number of sample units with this characteristic of interest, whatever that is. Being left-handed, having red hair, brown toes, whatever that characteristic of interest is, divided by n, which is sample size. Okay? So again, we're using the z-distribution, so I could easily ask you to do a traditional hypothesis test and or a p-value method test. So I think for today we'll just do one of each and see how it goes. Okay? All right, let's jump into the first example. All right, it says, from past records, a hospital found that 37% of full-term babies weighed more than 7 pounds. This year, a sample of 100 babies showed that 23 weighed more than 7 pounds. At alpha equals 0.01, is there enough evidence to say the percentage has changed? Okay, so as we go through this problem, and again, as a reminder, when you guys get to your test that we take, which is a very difficult test, you have to be able to distinguish between, oh, is this a test for proportion, or is this a test for mean, or variance, or standard deviation, or what, okay? So notice as we're writing out this problem that it doesn't give mean or standard deviation ever, but it does give a proportion or percentage a lot, okay? So the first sentence, from past records, a hospital found that 37% of all full-term babies born weighed more than 7 pounds. Okay, so the first statement says 37% from past records of all full-term babies born weighed more than 7 pounds. Okay, from past records, that's what we were given. This year, a sample of 100 babies showed 23 weighed more than 7 pounds. Okay, so here we have, this year, we have n is 100 babies, and then we had 23 weighed more than 7. Okay? Then it says that alpha equals 0.01, is there enough evidence to suggest the percentage has changed? So the question is, at alpha equals 0.01, has percentage changed? Okay, So this was our given from previous records. 37% of all full-term babies born weighed more than 7 pounds. Okay, so weighed more than 7 pounds, that is our characteristic of interest, okay? So we have a percentage of the population, and their characteristic of interest is weighs more than 7 pounds at birth, okay? Then this year, we have a new sample, 100 babies. 23 of them have this characteristic of interest, weigh more than 7 pounds. Now the question, alpha equals 0.01, has the percentage or proportion changed, okay? It doesn't say anything about average or mean or standard deviation, which is all over all the previous problems we've done, okay? Today's percentage proportion. Has the percentage changed? That is a z-test for the proportion, okay? All right. As I start to set up the test, step 1 is still the same, HO, H1. But instead of mu, which is a test for the mean, we're not doing a test for the mean, right? We're doing a test for the proportion. So you're going to put a P here for the population proportion, okay? The question that is being asked, that we're asked to answer, is has the percentage changed? Okay, it doesn't say greater than or less than, or at most, or at least. So this is an equals, not equals. It used to be this. Has it changed? It's not equal to this. Okay. So P equals 0.37. P not equal to 0.37. Okay? So this would indicate, if we go with this one, that it's changed. That it's no longer 0.37. Okay? Is everybody okay with the setup? So it's now based on P, not mu anymore, because that's a test for the mean. This is a test for the proportion. So P equals 0.37, P not equals 0.37. Okay, great. Step number 2, because the first HOH1 is equals not equals, what type of test is this then? Two-tailed, right. So draw your Z distribution. We have a two-tailed test. Alpha is 0.01, so that means we're going to put 0.01 total area. So each of these is going to be what? 0, 0, 5, right? Remember, alpha is the total shaded region. So if you have a two-tailed test, you have to split it in half. So we have 0.005. Okay, if it's a two-tailed test, therefore you have two critical values on the negative side and on the positive side. So you guys need to open up your Z charts, and we need to find these two Z values to correspond with 0.005 area. So I'll start on the negative side. I'll look in the actual area portion, and I'm trying to find the closest thing I can to 0.005. So 0.005, notice it's right in between 0.051 and 0.049, which is at negative 2.575. So everybody see that? So my negative critical value is negative 2.575, which means my positive is also 2.575 because of symmetry of the Z distribution. Okay? Very important that you can get that critical value, or in this case, critical values. Once I have that, I'm done with step 2, and I move on to step 3. Step 3 is my test value, and I just gave you that formula. Okay, so let's take a look at that. Step 3, Z equals P hat minus P naught divided by a big square root, P naught, Q naught, all divided by N. Okay, so I really want you to realize that that is the sample stuff. Okay, so today we had 23 out of the 100 babies that we looked at, so that is 0.23. So you could put 23 over 100, but that's the same as 0.23, okay? Minus the hypothesized value, which comes up here, is 0.37. Then a big square root. Now, if P naught is 0.37, what is Q naught? What is that relationship?
6.3.
Yeah, and how did you get that? 1 minus P naught, right? So this relationship still holds. If P is whatever, Q is 1 minus that. Okay, so you have 0.37 times 0.63 divided by N was 100. And I always mention be super careful plugging that into your calculator because you have a complex fraction and you have a radical. So take your time, split up the numerator and denominator, and let's see what we get here. .23 minus 0.37 divided by square root 37 times 0.63 divided by 100. Close your square roots. Okay, so about negative 2.8997. Is that what you guys got?
Yeah.
Approximately negative 2.8997. All right. Ooh, this is close. My critical value is at negative 2.5 and positive 2.5. This is negative 2.8997, so that is in the rejection region. Okay? So notice that test value falls in the rejection region. Because it falls in the shaded or rejection region, step 4 is you reject HO. If I reject HO, I'm going against this, and I'm going with this. And then in my own words, what happened? Previous records said that 37% of all full-term babies weighed more than 7 pounds. Okay? The question is, does it appear the evidence has changed? And yes, our evidence suggests that the percentage has changed. Okay? So to answer the question in our own words, yes, it appears percentage has changed. Any questions on that? It's just a new hypothesis test, but now everything is proportions instead of averages or means. Okay? So you have a proportion or a percentage, and you have a characteristic of interest. In this case, it was weighed more than 7 pounds. That was my characteristic of interest. Okay? And it could be anything. All right, let's do another one of these, and this was traditional method, let's also do p-value method, because you guys need to be able to do both, okay? So let's do another example with the p-value method this time. Alrighty, example number 2. A recent study found that at most 32% of people who have been in a plane crash have died. Wow, that's kind of depressing. At most 32% of people that have been in a plane crash have died. Okay? In a sample of 100 people who were in a plane crash, 38 died. Okay, so in a recent sample, of 100 people in a plane crash, we found that 38 died. Okay, the question is, at alpha equals 0.05, is the statement believable? Use p-value method. Okay. At alpha equals 0.05, is the statement believable? And they want you to use the p-value method. Okay. So again, let's just spend a minute or two discussing what makes this problem a proportion problem. Okay? There should be a couple of hints. Number 1, you don't see anything about mean or standard deviation. That's a huge hint. Okay? Number 2, it gives you a percentage. Okay? And then it says in a new sample, we have 138. So a certain percentage or proportion of this new sample has some characteristic of interest. Okay? In this case, the characteristic of interest is people that have died from being in a plane crash. Okay, that's what we're studying in this problem. At alpha equals 0.05, is the statement believable? So the question is the original statement believable? So that needs to be set up in my HOH1. And this is a little bit tricky because it's at most 32%. What is our inequality for at most? Less than or equal to. Okay, so the proportion is less than or equal to 0.32. If there's an equal sign, where does it have to go? HO. So that is an HO. All right, so we have HOH1. P is less than or equal to 0.32. P is greater than 0.32. This is the claim of the study. Okay? It has to go into HO because there's an equal sign with at most. All right. Remind me in a p-value method problem, what is step 2 in a p-value method problem? Go right to the test value. Okay? So you forget the critical values, pretend that doesn't exist, go right to the test value formula. All right, let's do it. So step 2, my test value formula, we just did one. Z equals p hat minus p naught divided by a big square root, p naught, q naught, divided by n. Okay, this first guy is from the sample. All the rest is from a hypothesized proportion. So this first guy is the 38 out of 100 that came from the new sample, okay? So what is 38 divided by 100? It's 0.38. Okay, you guys fill in the rest of this. P naught here is 0.32 divided by 0.32 times 1 minus 0.32, right, which is 6/8. And again, this sample was 100. Not every sample is 100. It just happened to be that these two problems both had a sample size of 100, but it could be anything, obviously. And let's go ahead and figure out what my test value is. Okay, see if you guys get approximately 1.2862. Approximately 1.2862. Okay. And that's the end of step 2. Now, step 3 in a p-value method problem is to find the p-value. Okay? To find the p-value correctly, there's a couple of things you need to know. First, what distribution, and it's obviously the z distribution. And the second thing is, was this a right-tailed, left-tailed, or two-tailed test? What is it? It's right-tailed. Okay, so I'm going to draw my z distribution. I'm going to drop down my 1.2862. Because our book only goes to 2 decimal places, I'm going to round that to 1.29. Okay? So 1.29 is what? Right here? And then because it's a right-tailed test, your p-value is the area to the right. That's very important. If it was a left-tailed, it'd be all this area to the left, but it's right-tailed. So this is my p-value area. Okay? So I need to go to my z distribution chart. I have 1.29. If I look up 1.29, it's going to give me area to the left. Okay? So you have to subtract that from 1. Or you could use your smarts and go to the negative side and look up negative 1.29, and that will give you the equivalent area, because that would be area to the left of negative 1.29, which is the same as the area to the right of positive 1.29. So that's what I'll do. I'm going to look up negative 1.29, and it says 0.985. Does everybody see that? So the area here is 0.0985. 0.0985. Okay? And that ends step 3. 0.0985. Okay, step 4. This is where I determine if I'm going to reject HO or do not reject HO, and that is dependent on if my p-value is less than or equal to alpha. Is 0.09 something less than 0.05 something? Is this number smaller than this number? No, right? 0.9 is larger than 0.05, okay? So because my p-value area is quote-unquote large, because it's bigger than alpha, we are not going to reject HO, okay? Because remember the statement is if your p-value is less than or equal to alpha, you reject HO. This guy's bigger than this guy, so do not reject HO. Okay? Remember, start this. If your p-value is less than or equal to alpha, you reject HO. That's how we determine whether we reject or not. If my p-value is less than or equal to, this p-value is bigger than, so we do not reject it. Okay, if I don't reject it, I'm going to circle this, and I'm not going to go with this. Okay? So I circled the claim. So the question is, at alpha equals 0.05, is the statement believable? And we're going to say, yeah. We're going with the claim. There's not enough evidence to suggest that the statement's not believable. Okay? So in your own words, yes, statement believable. Questions on this? Every day we meet, we're going to have a new hypothesis test. Okay? We've done the z-test for the mean, where you knew the population standard deviation. We did the t-test for the mean, where you didn't know the population standard deviation, and you had s instead. Today was the z-test for a proportion. Okay? So you have proportion stuff. You don't have mean or standard deviation, but proportion stuff. Characteristic of interest, how many out of the sample have that characteristic? Okay? Any questions?